Let's meet our friend Psi. Psi is a wave function, a mathematical object at the heart of quantum dynamics. He can be used to represent all sorts of things, like a literal electron in space or a figurative ball on a spring. As shorthand, to remind us of his vector composition, we're going to address him in a cat. Now let's say we met Psi at some time that we'll call t0. What information do we need to know where or who he'll be at some time t? The answer lies in the behavior of our other friend, Hamiltonian. Hamiltonian is an operator, someone who acts on a ket. Hamiltonian has a very special gift, so when they act on psi, they become a certain scalar times their time derivative, notated here with a little dot. Now setting this result equal to what we started with, we can perform some fancy footwork to get this time derivative of psi by himself where we can recognize something beautiful. The situation we're in right now, where our time derivative of a function is equal to some constant times the original function, has a very quick solution, indicated in blue. If we're clever enough to recognize how our situation matches this blue situation, we can extend it to create a solution to our own problem. This exponential we climbed through some hoops to meet has their own name, u. Where Hamiltonian tells us where psi wants to go, u will actually pull psi through time given a particular time interval. It's why their parents gave them the legal name time evolution operator. So how do our friends u and psi get along? Well, it can be kind of awkward sometimes, so let's hang back and learn from some other operator-ket pairings. These two are a great example. This Hamiltonian knows precisely what to do, since red psi is one of their favorites, an eigenket. They can act on red psi directly, and she will maintain her identity, only inheriting a scalar. Red psi is not alone in having this relationship with Hamiltonian. Here we can see her friends green psi and blue psi also share the special relationship with Hamiltonian. Hamiltonian loves these eigenkets so much, they can't help but see every other psi as a mix relative to how much a given non-eigenket reminds them of their eigenkets. In fact, each ket in this friend group is so distinct from one another, Hamiltonian can think of any given ket as a mixture of varying amounts of these eigenkets and act on each of them as we've seen before. But a non-eigenket simply doesn't have the same special relationship Hamiltonian wants to have, so their actions on this psi will leave psi a truly changed ket each and every time. Now, as we saw earlier, u's entire personality is just an exponentiated Hamiltonian. So if we know they're Hamiltonian's eigenkets, we will also know u's eigenkets. However, u gives different scalars to their eigenkets. Let's break it down. The scalars associated with each of these eigenkets are complex numbers, indicated here separated into their real and imaginary components. As u acts on their eigenket, they will twist and turn his or her scalars in a cyclic manner. However, don't be fooled. The size of this complex number, known as the modulus, will always remain the same. So now as our ket lives in an environment defined by a particular Hamiltonian, we can imagine a long line of u's evolving our ket just a little bit every second like clockwork. This will occur when psi lets time pass in an environment defined by u's defining Hamiltonian. As psi stays the same in this environment, the eigenket earns a new nickname, a steady state. However, not all Hamiltonians will appreciate our ket as an eigenket. Just like how our previous Hamiltonians would cause personality changes for our non-eigenkets, psi's evolution in an environment defined by an unfamiliar Hamiltonian causes periodic ebbs and flows in the scalars of our old basis kets, known as Rabi oscillations. However, if we give this Hamiltonian some leeway and see psi through their eyes, we can recognize our old basis kets as mixes of their own eigenkets. And just like before, an eigenket of our new environment is steady, even though, in the eyes of our old Hamiltonian, he is anything but. So next time we meet a ket evolving in time who appears to have no idea who he is or where she's going, let's borrow the eyes of another Hamiltonian. Recontextualized as a combination of another set of eigenkets, we might find they know precisely where it is that they're going.